Hi, and welcome to this talk on event sourcing for enterprise. My name is Ben Beattie-Hood, and this talk is the complete set of the course I have on event sourcing, which you can find on my YouTube channel. In this video, I'll cover some of the benefits of using event sourcing, how you can do it, how domain-driven design helps distributed system design, the principles events have, and the requirements they make of a supporting system. I'll talk through how to design commands, Readstores, and how to project across aggregate boundaries. We'll cover scaling, sharding, and replay. I'll give you some of the principles of aggregate design. And lastly, we'll wrap up with the pros and cons of event sourcing and recommendations for further exploration. Let's start with a very quick overview of what event sourcing is. In a typical system, we'd process and write to a database. And then maybe if we were eventing, we would emit events to communicate to other services what had happened. In this design, the database is persistent and the events are transient. Event sourcing flips this on its head. You can think of event sourcing as the derivation of truth from a stream of past events. If you can't derive your current state from all of your events, then you wouldn't be doing event sourcing. And so in event sourcing, it's the events that are persistent and the projected representation of those events is transient and it can be thrown away. And it's this fact that each of these projected representations is like a cache and can be thrown away that gives event sourcing its advantages when decoupling services and versions, etc. This might seem a bit abstract, so let's have a look at the way some business code or commands might affect state in a system. Imagine that we're inside our state store and that we're being told changes. To focus us on what we know within the state store, I've blanked out the acting code on the left to help illustrate how little the state store in a traditional application knows about what is happening. So here in the example, something is happening and the state store knows that a person's state is asleep and at home. Something else happens, nothing is clear to what is happening to the state. Again, another thing and the state hasn't changed much. Another. And finally, another thing happens and the state changes. It's unclear how or why, but we know a little bit more about what is happening. Again, something happens. Another one. It's quite blank, isn't it? The state clearly isn't aware of the data outside of what it's designed to hold. This might sound legit, but the problem here is that if we want to refactor the shape of the state to be richer, we have to change it quite a lot. And sometimes it's impossible to refactor this old state because the data for the new schema simply isn't available. So storing only current state could be considered dumb. And I mean here, it doesn't show why it happened to get to a value. It just shows the flat answer of what the value is. And so it's very hard to change the shape of that answer because there's very little additional data to enrich it. Let's have a look at the same example again, but including the original commands on the left. You can see now there's a lot more rich data on the left in the sequence of the commands, which we are scaling down when we store it only as simple current state. Another. The state continues to be quite dumb, but the commands here are rich. Another. So what happens if we kept this richer data on the left instead of just the state? You can see now it's not just the what, but the how or why something has reached a state would be recorded. So as we learn more about our domain, if we're translating data simply into current state, we're often throwing data away. Instead, persisting the why we got to a decision is far richer and far more powerful than storing only a transient point-in-time result of a decision. Storing richer data instead allows us to rewind time and change the way we represent state by what's called replaying the events. Now let's try this again. Let's imagine we stored the left-hand side state as events, and now instead of a simple state in perhaps a table, we want a more detailed graph representation in our system. If we kept only the flattened state from the right, it would be really hard to refactor this state into a graph shape because we'd be missing the richness of the data from the left. But instead, storing the events from the left, it's easy to reproject into a state as a new richer shape. Replaying the events to create a new shape as a time graph, we can see the kind of extreme refactoring we can go through on past data. There's no way I could refactor like this if I had a simple state persisted. But instead, persisting what has happened as events, I can replay these out to a much richer state as we go back over them. Next, another. And instead of now knowing just that someone was awake and at the station, in the first example, I now know much more about this person. But I did it all by replaying existing events, rather than starting from a dumb state. My project kept the richness that I could translate, and so my old data has immediate business value. In conclusion then, relying on state gives you your current representation of the facts of a domain, and relying on events gives you the ability to reshape the history of those facts as your domain evolves. You can leverage data more quickly and adapt more easily. There are other advantages, such as decoupling via events rather than APIs, and there are a few ways to do that, and we'll get into the other advantages in a bit. But this here is unique to event sourcing, the ability to update your state as your business needs evolve. Let's take a break now and answer a question I'm sure is brewing: data storage and processing. Surely it would take a crazy amount of disk space to store every event that has ever happened. Actually, it's relatively easy to store the events, for example on Amazon S3. Remember, events are tiny, perhaps between 1 and 3 kilobytes, absolute tops. And they're also immutable, so they can be appended to a log in a forward-only manner, with no gaps, and so repeated data is easily compressed. So to give an example of a production system, perhaps storing about 1,500 events per minute, at worst that works out about 200 gigabytes per month for all production data, which on Amazon S3 is about $4 split over standard and standard infrequent access storage. So storage really isn't a problem. Now let's tackle another concern. Surely it would take a long time to reprocess all those events every time you want to make up a new state. In practice, instead, you can use snapshots to speed this up, and we'll get into those later. But in truth, yes, to recalculate the current state can take a long time. But it's not as much as you'd think. The unidirectional nature of a system means that in-memory read stores calculate way faster than you'd think. Even using disk-persisted key-value store will allow you to process over 1 million transactions per second per node, and a SQL store would allow you more like 200 to 500 per second. But yeah, the truth is, replaying events, if you change the way you represent state, can take time, but in practice, this works out as an okay thing. Let's pause for a minute and look at how this replay process works. Here's your event stream and the state calculation. Now, say you want to change the way you calculate state. You want to change one of the data types for a field, or even go as drastic as our previous example and move to a different type of state, like a node graph. Remember, these events are persistent, and unlike the traditional system, the store is the transient part. So we can throw the store away. But what happens when we do that, when we delete our state and start again? Unfortunately, discarding your current state means that your users get an error when they try to access it, because it takes a little while for your replay to catch up. So what do? Instead of deleting existing state, we can leave the existing version intact, live and receiving events. But we can also begin reading the stream of events live into a new version. Here I've called it version 2. Gradually, the new version will come up to position and can be A/B tested alongside the live existing version. And then, when it's fully up to date and verified as working with your tests, you can swap it to be primary. You can still keep projecting out to both V1 and V2, and you can try canarying some users over to V2 before transiting them all over to it. And when you're happy and that V2 is working well, you can safely delete the old one. Zero downtime and a canary swap over, because users have already been accessing the data on V2. So even if the replay can take a while, deployment is still immediate, and it has the benefit of allowing pre-release A/B testing on live. This is a nice segue into the why bit of event sourcing. The main advantage of event sourcing is that you decouple from dependency on state representation. When two or more systems are dependent on each other's state, you can consider your system logically a monolith, distributed or not. It's a single system. Whereas we saw in event sourcing how easy it is to completely revise our state because it was not coupled to nor considered the source of truth. Now this means that you can move more rapidly and refactor more quickly, which in turn allows you to be more in tune with your customers. This customer delivery aspect of event sourcing is often overlooked and underrated. By staying nimble in your data, you stay closer to your customers' evolving requirements, allow experimentation and A/B testing, and can change as your market evolves. Conversely, in say a more traditional shared state database like a SQL DB, how easy is it to deploy or roll back without losing data from a change to a table? Maybe it's tricky, maybe manageable, but how about if you notice that bug a few months down the line and you've already lost that data? With event sourcing, your current state is a fold of your events. With this term fold will come up a bit in this talk, and I want to show you now what I mean. You can consider state to really just be a fold of all preceding events. You can imagine it a bit like this. The term fold is supposed to imply that no events are missed and that every event is folded into state in order. This keeps the logic to calculate state, or the effect of an event, at the absolute minimum, allowing easier encapsulation of logic. We'll dig into this a little bit more later, but I just wanted to show you what I meant by folding. So back to the why. Folding means your state is just a cache of your events folded to a given point. So your projections are stateless and therefore are decoupled. What are some of the other advantages to event sourcing? Debugging is much easier because you can rewind time and see exactly what the user saw. This is otherwise nearly impossible to do in a distributed stateful system. In short, it means you can play back events locally with an audit trail of cause and effect. Deployment is not only easier to do, zero downtime as you switch between versions, it is also more reliable because you're less likely to roll back, because you're able to A/B test your changes in live by default. I know I've spoken a little bit about this in the past, but it's really important. When you design functions around immutable data, it's easier to test and reason about those functions with no side effects. And it's the same with event sourcing. It's largely a set of pure functions at an architectural scale, which means it's easier to decouple them and reshuffle them, and easier to test them without scaffolding or mocking. We've spoken about this earlier in the talk, and the safety and zero downtime switching it provides. Events are appended live even while you're deploying your changes. You can also direct a percentage of your users across to your version 2, so you can canary test it in live against real users without affecting your system adversely. You can add new state calculations after the fact. If you're storing business events, you're less likely to be throwing data away. The richness of your source data and the limited dependencies on state help us enrich refactored models with no downtime during deploy. These are the advantages of event sourcing. So how would you build something like this? I had a few examples of lessons learned, and I wanted to trim down this talk, so I've just reduced it to the principles you need to know. It's that bit that's the most important anyway. So in answering how to build it, let's turn to a system design principle, CQS, or its implementation for distributed architectures, CQRS. Now, CQRS is a system designed around the separation of writes, which have a high processing requirement, from reads, which have instead a high volume requirement. When you're writing to your system, you're likely to do verification and validation that requires processing. And when you're reading from your system, you're likely to do it in bulk across many users, so it requires high volume. CQRS separates these two responsibilities and designs around a system which is termed eventually consistent. You see this design in distributed systems regularly. It's the idea that you put something somewhere, but it might not be available until the read node you're connecting to has caught up. Think of it as everything as a synchronized cache. The benefit of eventual consistency is it allows the separation of write and read requirements, including scaling, into dedicated systems. I'm going to go into a bit of detail now on how you build something like this in the simplest possible way by following domain-driven design principles. If you've watched the talk that I did on structured event storming, this might seem familiar. These are the main components of domain-driven design for events that we have uncovered: the commands and their associated validation, events, questions, and answers. In that talk, I covered a simple method for using these to validate an understanding of domain flow with the customer, business, design, and dev teams. And we saw how we can translate these directly into event-sourced implementation, each part matching one-to-one to the final design. We'll come back to this detail in a minute, but in summary, this reference architecture is known as CQRS-ES, or the event sourcing branch of CQRS. Before we fill in the detail, we first will do a quick recap of domain-driven design for distributed eventing architectures. This is the most important part of this talk. Event sourcing is a powerful tool, and you can create enormous problems with it if you don't understand the principles behind event design. You can consider event sourcing like splitting the atom, and we need to make sure we don't make a weapon of mass destruction. If you've studied domain-driven design, you've probably heard of a bounded context. It's a piece of the business that uses a ubiquitous language. A ubiquitous language means the same term is given the same definition by all using that term. If you're in a happy situation where the whole business uses a single ubiquitous language, then you've got a single bounded context. This bounded context directly affects your understanding of the domain's aggregate and the business's processes around those terms, so it's important to define. Inside a bounded context, you have aggregates. No aggregate crosses a bounded context boundary. The term aggregate means a collection together of values. The aggregate contains one or more business entities, representing the terms and processes within a single transactionally validating piece of your business. Each aggregate represents a transactional boundary for business processes. Inside each aggregate, you have entities. Entities are how the data is stored within an aggregate's transactionally consistent boundary. Some may be siblings, some nested. And so in DDD for event sourcing, you store the events at the aggregate level because they relate to business transactions. Event data may therefore apply to several entities within an aggregate, but the contract is that events leave the aggregate in a transactionally consistent and valid state after being applied. So you have no validating transactions that span events. Here we have the first rule of distributed eventing, and it applies to event sourcing too. Events must leave the aggregate in a transactionally consistent and valid state after being applied. There must not be validating transactions that span events. This rule of events in distributed systems will drive most of the principles I'll cover now regarding distributed system design. Let's list these principles of event design as we go. The first one we've got already. Events are the transactional transitions in a distributed system. Event sourcing is a distributed system that has multiple parts, and so an event being the transactional boundary really helps. Examples of events like this in a banking domain might be new account application received, customer identity verified, account opened, funds deposited, funds withdrawn, account statement issued. And here you might notice that the example events I'm giving are business events, not CRUD ones. So the second principle is that events must hide state. The primary benefit of event sourcing I've shown so far is that it allows you to refactor state easily. Sure, there are heaps of other benefits, but this refactoring is the main one. If your devs can evolve your product as quickly as the customer evolves their practices, then you can practice DDD. And if you can't, you start to sink in unused features. So if you have event sourcing that will allow you to refactor state super easily and then expose your state in the events as CRUD events, you're basically shooting yourself in the foot. Your state, which you wanted to refactor, just became public. Everything in your domain, and possibly outside, may then depend on it. So it makes it very difficult to refactor. And it also is less likely to represent a business transaction or more likely to span transactions. The practice of carrying state in events is called event carried state transfer. Some systems are built on it, but they shoot themselves in the foot as soon as they do by coupling the systems together, and I would recommend you do not do it. Do not expose your state in your events. Events are your points of contract. Refactoring them is hard. The next principle of event design is that your events should represent business transactions. By this I mean events should be modeled in your software as similar as possible to how you have discovered they are communicated within the business domain. There are two sides to this. Events are hard to refactor because they are persistent, but your business is less likely to want to refactor them than your software. So making your software as similar as possible to your ideal business state is the safest way forward. The second reason is that business events are more likely to represent the value your customer is trying to derive from your system. When building software, it's better that the bits that cost more are the ones that the client is interested in investing in. Business events are more likely to have richer data too and allow future reprojecting. And lastly, refactoring business events is less likely to happen because of engineering reasons and more likely for business reasons, so it won't happen as often as you scale. And so the third principle is to omit business events, not CRUD ones. The next thing about events is that they must be valid. If you store a payload that is not validated, it's not a record of a business decision, it's just an intent. Intents should be represented as requests or commands. For example, please try to do X. In contrast, an event should be a record of a thing that is valid and has been done. As such, all events must be valid. This takes us to our principle, which is the correlative of that previous one. How do we define a valid event? Well, it's valid against some existing state. State in turn is known to be a fold of all events up to the current head event. Therefore, guaranteeing the order of events is essential to assisting that the event is valid to be appended. Let me give you an example. Let's say this is my event stream one morning. I woke up, I got dressed, went downstairs, and now let's say I want to append an event called went outside. Is it valid I do this? Sure, because I know that it's okay to append because I'm dressed and downstairs. But if I haven't got dressed and gone downstairs yet, then I shouldn't go outside. Ouch. And so there's not much point in me getting dressed then either. You see, the validation of events is very much tied to their order. You don't know if an event is valid unless you know its order. Without ordering, you start to undermine the business nature of your events too, and may need to omit state or cruddy events to assert compensating values. Order is a really good guideline in event design, as well as crucial to the validity and therefore actual nature of events. What next? The last 3 rules of events I've found are more specific to event sourcing, and they are perhaps more obvious. The first is that they are persistent and immutable. When you treat events as your source of truth, they need to stick around. It doesn't do well for a system to lose truth. Any stream of events must be available. Any downtime on your event stream can affect listening or replaying projectors. Therefore, it helps to use a highly available store, which is quite easy because the events are immutable and can be replicated between nodes. Lastly, they must be typed. By typed, I don't mean quite the same as types in a coding language, but rather that the consumer must know the purpose and therefore the assembly version and type of an event. We'll talk about version migration later, but for now, let's get back to our reference architecture. We now have a solid grounding in event design for distributed systems. We know that events need to be per aggregate, representative of an atomic business operation, valid and therefore ordered, persistent and immutable. So what is this bit, and how can it produce events like this and fulfill those requirements? Here's what that part needs to do. It needs to take a command on the left and write events to an aggregate stream on the right. In practice, there are 3 steps to this. First, the command is passed to the first step, which loads the validating state and version, usually from a cache like Aerospike or a stable Redis, but if unavailable, it can recreate the cache from a fold of all the events. Remember, the validating state includes the ordinal of the last event folded, the head event. The next step checks that the command can be applied given the loaded state. So in this example, it might check if the basket has already been checked out, and if it has, instead return an error. If it's valid, then the last step does a conditional write. It appends one or more events to the stream with the assertion that the stream's head is currently still at the version loaded in the validating state. This basically checks that nothing else has written to the aggregate stream whilst the command was processing its logic, and so it is important if your event stream is highly concurrent. If it was successful, the command should return a success code, including any IDs generated, including the version of the head event. But what happens if something else did write to the stream and appended events at the same time whilst we were processing? Well, this conditional write fails, and we flip back to the first step and auto retry. Loading the new state from the cache, we check if the command is still valid to be processed, and then, if so, the events are conditionally appended again. This means that your commands and validating state allow for a highly concurrent stream, while also preserving the rules of events that they must be valid before appending to the stream. Appending invalid events to a stream, even if you append then corrective ones later, can cause downstream complexities and loops that are easily avoided with this simple pattern. So what then are the rules for command design? They need to have context, for example the logged in user, etc., and be validated for that context before they run. They need to validate that they can run given a version state. They need to transactionally append their events at a specified head version, and they need to support failure of this, so be rollbackable and repeatable. Therefore, they must be pure. They cannot have side effects. So they can essentially be represented as a function of validating state and version plus context to outputs, new validating state, events, and version. Great, now we have explored all the base principles required for event production. That's the first half done. How about this part? This has a couple of rules too. The place to start is that these read stores are projections designed to answer read queries from your API. One way of thinking about these is, what data would I need in an API response if I just wanted to call the API once per page or component load? It's not the only situation these read stores are designed for, but it might help relate the wide expectations you can have of your read stores. So, does this then mean we have duplicate data within the read stores? Yes, but it's a lot less scary than in a traditional database, because there's a great pattern for updating this data that means all data automatically synchronizes eventually. As each aggregate instance causes a discrete stream of synchronous events, I'll assume for this example that I have here a single aggregate stream. If you're grouping streams for transport, either by aggregate type or by topic, you may need to include the topic offset as well as the event version in the following example, but the overall design you should use is the same. So here's an aggregate stream of events, and the next event in the stream is being read by our projector. It's called a projector because it projects a fold of your events into a non-aggregate form like a SQL store, cached document, or node graph. Once the projector has read the event, the projector loads the current projection for the correct aggregate from the read store. The projection, like the validating state, is marked with a version of the last event appended to it. The projector folds the event onto the projection's data and updates the version number. Lastly, the projector writes the projection and its new version back to the read store, ready to be read by any queries. The projector then increments its event bookmark and continues to the next event. When a projector starts up, it loads the current projection from the read store and skims ahead through the persisted stream until it reaches the next applicable event. So what happens when you need to recalculate the state into a new shape? Well, you just delete the projections you want to replay, restart your projector, and then it will run from the first event again because it has no bookmark, this time replaying the events into a new representation. So when a write happens at the top, it might take a few milliseconds before that event data is projected to the read stores. This is called eventual consistency. The problem with eventual consistency is that subsequent reads might not return that data immediately if it has not been projected yet. The key to getting this working nicely is in this version data on each event. When your command from your write API at the top here originally writes the events to the stream, in this events 1 through 4, it needs to return the version of the last event written. Then the write API returns this head version back to the originator. Now that the originator knows the version, they can check this against the version info returned on a read API response. If your reads depend on the latest version, they can poll your read API until that version shows up in your read stored data response. Now we'll continue with the example to show the projector processing the events, projecting them to the read store, and the read API continues to poll until the needed version is available. So in this way, using the version information solves the cache invalidation problem. Happily, this fits well with an HTTP concept called e-tags. E-tags are an HTTP header of a unique value that form part of the cache invalidation for HTTP GET requests. This directly correlates to the version data for the event and read store. So posts, puts and deletes can reply with the e-tag, and gets should include it in your HTTP headers. By using the HTTP e-tag to store your request response versions, you get support out of the box for HTTP caching. So what could these read stores be? Document stores like DynamoDB, Raven or Mongo, data warehouse star schemas like Redshift, relational SQL databases, node databases, GraphQL stores and feeds, ML models, and even web APIs, so long as they're resettable. And this is the one I find most interesting, because one such possible API is the write API of another domain. And now things start to get really interesting. The pattern of consuming from one event stream and projecting to another write API is called an interpreter, and it lives within the receiver's domain, shown here at the bottom, listening to events from other domains and triggering its own domain's commands. The reason it calls its own write API commands, rather than directly writing events to its event stream, is so that it remains subject to the same validate and emit concurrency logic that is used by the commands. And so any validation failures should be logged by the interpreter and remedial action either automated or manually undertaken if needed. Interpreters are a way of listening to events on other domains and taking action in auxiliary domains. Similarly, you can also use an interpreter to call your own write API, again, enriching events. For example, maybe there was a login event with a user ID in it that could be enriched with data about the username or location. Or perhaps there's a purchase event which could be enriched with analytics. Enrichers are a way of doing in-stream processing. For me, they've changed the way I think about enterprise architecture because most domain actions can become simple interpreters between event streams. Conversely, I've seen some companies fall into a pit by writing events directly back to their stream without going via commands. And while it seems simpler, it fails because it is the commands validate conditional append logic where concurrency is resolved and domain validation is encapsulated. So now we've explored all the design guidelines around event handling and projection, both within and outside a domain. Lastly, we need to touch on sharding and scaling. The beauty of eventual consistency is that each of these components is free from being within a shared transaction, which allows them to shard and scale independently and asynchronously. So what does that mean for the operation of aggregates within streams? The key to scaling using event-sourced aggregates is that, like I mentioned earlier, every aggregate instance can be considered its own logical stream. Events on an aggregate instance are synchronous within the aggregate instance, in order, but events on different aggregate instances are asynchronous to each other. This means you should use your aggregate instances as your scaling mechanism. As long as each aggregate instance is handled by a consistent shard per component, everything works perfectly. The simplest way of doing this is to use modulo. Say we've got a stream of events coming in, and I've scaled up to 3 projectors, ID'd 0, 1, and 2. When each looks at the event stream, they check first the aggregate ID. Then they use the modulo operator by the total number of projectors to determine if they need to handle the event or whether it will be handled by one of their siblings. In this case, aggregate ID 74382 mod 3 is 0, and so it's the first projector that handles the event. The next event for aggregate ID 43894 mod 3 is 1, and so that's handled by the second projector. Please note, I could have scaled my Readstores similarly here, using the modulo to select the Readstore shard to target, but for the sake of the simpler model, we'll just keep it to this one projector component. This sharding by modulo is applicable to any of the components because of eventual consistency, and their scaling is independent and asynchronous to one another. It's worth mentioning that when you have multiple streams and multiple projectors, it can be helpful to use a high-performance system like an actor framework to manage the actor states. I've not found this necessary with the number of events in smaller systems, but I have an open source project called Sunergeo on GitHub, which explores how this part of the scaling system works if you're interested. As you may be able to guess, this sharding is subject to a brief pause during the draining of current work if you need to auto-scale up or down, otherwise you get overlapping ID modulos. But this can be mitigated by draining per aggregate instant. As a separate project, I've been working on an alternative scaling method using a scaling modulo broker, which doesn't require draining, but that's outside of this discussion. Whichever way you do it, sharding allows you to put in auto-scaling mechanisms for any of the independent components of the system based on metrics like queue length, backoff, and workload. Now we've covered the hardest question in event sourcing, which is what are the underlying principles and how should they play out into system design to allow scale in production. There are a number of pros and cons to event sourcing, but the core of this presentation I'm trying to focus on are these principles around domain design for distributed event management, because easily the largest hurdle faced by dev teams considering decoupling by events is the design of events and their aggregates. Where are the boundaries? What are the business transactions? And how do we keep from exposing state? So one last bit before the pros and cons. I'd like to give you 4 rules for aggregate design. These are from Vaughan Vernon's excellent book, Domain-Driven Design Distilled, which I think is a great summary of how the principles of distributed event design play into DDD. So what are these last 4 rules of aggregate design? The first rule is that you must protect your business invariants inside your aggregate boundaries. This means that you should ultimately determine aggregate compositions based on what must be consistent when a transaction is completed. This is why we've talked about events which represent transactions always being at the aggregate level. The second rule adds the inverse tension, that the memory footprint and transactional scope of each aggregate should be as small as possible. This brings in the single responsibility principle. If your aggregate has more than one responsibility, it may be beneficial to split it up. This plays a healthy tension with the first rule, and together they help define what is included in your aggregate. The third rule is that you should reference other aggregates by unique identity only. For example, a GUID or UID instead of an integer. This allows support for eventual consistency. You can store a relationship before the recipient of that relationship necessarily exists. This plays into what we discussed about event design, where you should use GUIDs to reference other aggregates if necessary, rather than bloating your events with data outside your aggregate's responsibility. The last rule is another way of looking at the third rule, and these two again play together. You should update downstream and sibling aggregates using eventual consistency, and for siblings, you therefore may need to store their head version on your aggregate. Please note that topics avoid the need to store the head version. These four rules from domain-driven design distilled largely center around transaction boundaries and support for eventual consistency, and are correlative to the event principles I've highlighted in this talk. DDD and event sourcing are symbiotic and are a really flexible way to build systems. So that's it. In this talk, we've looked at what event sourcing is and some of the benefits of using it, how it relates to domain-driven design and how it builds on the CQRS principle, the principles needed to build for scale and how to avoid common pitfalls around coupling, concurrency, etc., how to apply these principles when creating the necessary building blocks such as the commands, conditional writes and sharding in event storage, projectors and Readstores, and lastly, how these components work together using DDD to allow for eventual consistency, handle concurrency, and allow for replay and scaling, and some of the safe principles for decoupling using DDD. Using DDD at this architecture level enables you to flow the business domains and values easily down to every level of your software. It encourages code that is expressed in business terms and follows the business's ubiquitous language. And it follows the seams in the business for distributed transactions. I'd recommend using structured event storming for the discovery, as it will keep you closely aligned to the business's perspective and give you insight into values and coverage. Refer to my tutorial on YouTube if you've not already seen it. The key concepts in your business are likely to stay more stable than your engineering concepts. Engineering is always a discovery process, and so you should try to stay as close to the business domain as possible, as you don't yet know what you don't know. You're now also including time in your domain modeling, which means your model is more like the real world. And as you're including time, you can add more value than a simple CRUD store, as you can now do behavioural analysis. Behavioural analysis is the processing of a time stream to identify important changes. When you have the richer data and you store the time sequence, you can bring much more value to your business. This, along with not throwing away data you don't know the value of, is a really important pro to event sourcing. So all this given, what's the catch? Why isn't everyone doing this? There are some hurdles to overcome when adopting event sourcing, and how challenging they'll be to you will largely depend on your organisation. The main one is that you have to change the way you think. We're used to designing with objects and transactions. We now need to design with transformation and eventual consistency. It allows for a simpler resulting codebase, more focused on business logic, but changing the way devs think has been, in my experience, easily the trickiest hurdle, and it was the thing I found most difficult myself in getting to grips with it. The cost of mistakes that comes from changing the way devs think can be high, and as you learn through it and get to grips with it, sometimes there's a tendency to keep one foot in both camps, some monolithic or CRUD transactions with side effects, and some pure events and eventual consistency. But trying to do both can cause unnecessary complexities that you later have to unwind. But worse, trying to do both can cloud your domain logic, separate you from what the customer is trying to achieve. The second hurdle is that while event sourcing makes refactoring state easy, refactoring the event is much harder. And as you explore your domain, this is the place you're most likely to screw up. Getting your event design right directly affects your velocity. In traditional systems, it seems you can hide bad aggregate design for longer and avoid it with additional code. But with event sourcing, mistakes are much more easily visible, which can be a good thing, but it takes getting used to. Again, I'd recommend my tutorial on structured event storming to avoid some of these early mistakes in getting your aggregate and event data correct. The last hurdle is that it's not mainstream yet. Debugging, tooling, etc., there's not much there. Most of the documentation on MSDN or Stack Overflow, etc. is dedicated to objects and storing data in traditional databases. There's not much out there about event sourcing. AWS is the same, more messaging, less eventing. So it's cutting edge, and without tools like the principles discussed here or structured event storming, it can easily go awry. If you're interested in the subject or looking to build out an event-sourced system, there are a few topics I'd recommend exploring further. Using topics and aggregate groupings for transport can help decide additional storage and transport requirements. Bookmarking alternatives, and I've used 4 different bookmarking strategies in the variants I've been refining, per aggregate, per topic, global and queues, all with their different pros and cons. And while I've settled now on the one discussed in this talk, I'd recommend considering it an open question. There are a few books and talks available on event storming, and I'd strongly recommend looking into this to better clarify your events before getting started. And we've touched on basic scaling via sharding in this talk, but there are several ways to do this, and there are a lot of resources available on this topic. I've recently been working on a way of auto-scaling that complements this, and I'm happy to go into details of this outside the talk. Also, back-off strategies can be tuned per aggregate or per shard or region, but those are more advanced topics too. Other than this, that's it. I hope you found it interesting. If anyone has questions, you can contact me via Twitter or LinkedIn. Thanks for your time, and all the best for your next event-sourced project.